You know, figuring out this business about what exactly the subnet looks like and how it's structured is a lot of work. It's tough when everything just seems to be scattered about with little rhyme or reason and you can't put your finger on where any one place might be. So maybe it's best that I chip away at this question slowly by asking another question first. How big is the subnet? Maybe if we can get a sense of how large this place is, in a sense, then that'll help us answer some questions later down the road. But it's going to be difficult for me to tackle this question by myself, too, as I don't even know where to start with it.
I might be able to help with that. Hello.
Greetings, comrades! Apocrypha here, and today I've happened to stumble upon a fellow comrade in my ventures through exploring this place. May I introduce you to Little Tornado, who I'll be working with on today's episode. LT, how are you today?
I'm doing well, thank you. I think it's a miracle in itself that our sublayers just happened to overlap enough for us to be able to find each other. And I've got a lot of thoughts on my mind when it comes to trying to answer this question that you posed earlier. How big is the subnet?
Well, good. I suppose it would be beneficial to start off with a few guidelines that we'll have to make before we get into the cold calculations, just so we don't get too far off track and confused. I was thinking that we should keep in mind these parameters and assumptions.
Actually, Apocrypha, the answer might be easier than you think.
What do you mean?
Well, technically, this question has already been answered by Mateusz Skutnik himself, or at least, in part.
Oh. What did he say?
It's very easy to look up. In a forum post from August 16, 2007, Matt wrote in response to how big the loop was. He said just one word: infinite. Since the loop is at least partially related to the actual subnet, then any number of real locations we added would be adding to an infinite number of screens. And therefore, our answer would still be infinite. Plus, you have to consider the wild mass of mutated submachines that are growing beyond the outer rim. Those locations and their size are simply incalculable.
I see. Huh. Now, but in all seriousness, with that in mind, I still think it would be interesting to discover how large the subnet that we know is. That is to say, all the locations that we've visited before, and even going so far as to predict how large the others may be that we haven't found, and just get a good rough estimate for how far we can calculate before our numbers start getting too messy. Do you agree that we can still do work in that sense?
Of course we can. It might be a wild goose chase, but at least we'll get somewhere and walk away with some sort of number in our heads to use any time we want to even start hinting about how impossibly large this place can be.
Well, good, so let's establish some guidelines. Here's what I've come up with so far. Number 1, let's not talk about the loop. At all.
Enough said. Carry on.
Number 2, let's also not worry about layers, because I don't know to what extent these locations will overlap each other, and if the layers 100% match up to the same physical space between them. So maybe it would be useful just to sit down and look at these locations and calculate how much volume the cubes take up, without worrying about navigators or knots or any of that jazz. While we're at it, let's not even try to talk about the T word.
The T word?
Yes, the T word. Time.
Yeah, let's not go there.
Good. Do you have anything that you'd like to add?
Well, it might be good to take conservative estimates of these sizes, which means tending to underestimate instead of overestimate. I have a feeling these numbers are going to get quite large either way, so let's try to make them smaller so we can minimise our descent into craziness. But who knows, maybe we'll abandon that idea and see where the numbers take us.
Yeah, I think either option is fine for us, and I think that will just about do it for our guidelines. So, where to start?
I suppose the obvious will do. We have to get a sense of how many different locations there may be, and we can start this counting with the XYZ coordinate system.
Good plan. As we know, most of the locations we visited contain XYZ portals, also known as lab portals, and these portals have 3-digit counters that range from 0 to 9, each one a unique coordinate for a different location. So the total possible range of any location coordinate is from 000 to 999, which gives us 10 cubed or 1,000 different locations to start with. That's pretty easy. Now, just because the portals go up to 1,000 different locations doesn't mean that there aren't more. These are just the ones that we, Martau, and the exploration teams were able to reach, presumably after they figured out how to reverse engineer these portals from the original prototype seen in the Edge. We still have so many more to talk about.
Yes, and that means talking about the next iconic symbol of the Submachine series, besides lab portals, which is karma portals and the locations they are connected to. Now, the number of possible karma portal locations is much more difficult to calculate. not because the way that I have planned is particularly difficult, but because we're not exactly sure if we should use it. As we all know, karma portal locations in the Submachine universe have their own coordinates as well, but these are written in the form of 3 letters, not numbers. However, it's also made clear that the meta coordinates for each karma portal location are not nearly as randomly assigned as they are to XYZ coordinate locations. For example, you have locations like CAT, which have a theory about Einstein the cat. Location LCR has an excerpt from the author H.P. Lovecraft. OTT was designed by a person named Hannah Ott, and then you have ones like MNT, which is, very clearly, a mountain. So it's not proven that it would be a good idea to assume that there was one karma portal location for every combination of 3 letters. But let's do it anyway.
I like the way you think. Let's use the same method from before for the XYZ coordinates but apply it to karma portals. Assuming the karma portals are made of letters from the English alphabet, instead of having 10 cubed locations, the number of karma portal locations alone jumps to 26 cubed locations, because there are 26 letters in the alphabet.
However, you're forgetting something. We have one karma portal location that drastically changes that number, V12, or V12, named as such to reflect the name of the author of the location theory. This has both letters and numbers, so taking into account the 26 letters of the alphabet and the 10 digits, that gives us 36 to the 3rd karma portal locations, total. Am I missing anything?
Just one thing. If that's truly the case, and assuming that none of the karma portal locations are also lab portal locations, that means that the lab portal locations are included in that number 36 cubed. So we'll have to subtract them out, which means taking out all the combinations that result in 3 numbers. That means that as long as we have at least one letter in the coordinate, it's a karma portal location. So the math isn't 36 times 36 times 36, it's 36 times 36 times 26, or 36 squared times 26. And that number written out is 33,696 possible karma portal locations. The numbers are already starting to add up.
Okay, so we currently have that many karma portal locations and 1,000 separate XYZ portal locations. But we're not done. Not by a long shot. Because there's another type of location we must talk about. Locations connected by root transporters and cipher plates. And I believe this is where things start to get a little tricky. The problem is, there are locations in the Submachine universe and Submachine 5 the root that both have root coordinates and XYZ coordinates. Just by looking at the subverse itself, you'll notice that not all of these appear to be part of the same transporter network. Some of these root transporters look sort of the same, but most have different colours, different textures, and even different signs of age, wear and tear. And in the Submachine universe, there are 9 different transporters that we see, including the one from Sub 5. So the question is, do we treat these all as separate systems, or as the same system?
I have an idea. Let's meet in the middle and group together the transporters that look similar, that might be a tad objective, but it's okay, and group them together under one system. Doing that, we see that 9 potential systems can be condensed into about 6. Now the question is, how many locations does each system have? And for that, we have to turn to
the cipher plates. We need to figure out how many cipher plates a system holds. Fortunately, in locations 552 and 553, we can see where cipher plates are stored. We can assume that these cabinets hold plates that are all unique, as it is implied from a secret note we find in Sub 5 where Matt talks about 6 separate cipher plates. But here, in 553, we can see storage for 12 different cipher plates. So I'm willing to bet that, assuming these are part of the same system, the locker we found in 552 allows us to explore a subset of the total number of locations for this area, using a possible 6 cipher plates out of 12.
Very good. Would you mind answering the age-old question for us? The age-old question being, how many locations are there in a cipher system?
Well, the simple rule to follow is that since each transporter we run across is assumed to have exactly 2 slots for plates, then the general formula for figuring out the number of locations for a system is n squared plus n plus 1. So for a system of 6 plates, the number would be 6 squared plus 6 plus 1, or 43. For a system of 12 plates, the total would be 12 squared plus 12 plus 1, or 157 different locations. 157 locations for one system! That means for 6 different systems, as we determined before, we multiply this number by 6 to get 942 possible locations with root transporters in them.
Now, if I understand correctly, we've only been able to group together 6 different transporter systems because that's all we've happened to see, but we don't know how many more might be in locations yet undiscovered. After all, at the time of talking about this, we've only discovered 79 lab portal locations, so I propose that we get a good estimate of how many more root transporter systems we might be able to find out there in the near or far future. Let's divide the number of transporter systems found already, 6, by the number number of total lab portal locations, 79. You'll notice that I'm not including karma portal locations because no root transporters so far have been found in karma portal locations at all. The simple use of proportions lets us see that we can expect in 1,000 different XYZ locations, we can expect to find a total of not 6 separate systems, but instead 76 different root networks. Believe me, I double-checked the math. So going back to our original number of 157, we have to multiply that by not 6, but 76 to get a new estimated total of 11,932 root transporter locations. It's freaking unbelievable. However, this number has to be trimmed down a bit because, as we've talked about before, some of these locations do show up in already seen locations. So we have to subtract a certain number of locations so that we don't accidentally have duplicates. The way to do this is similar to before. We take the ratio of the number of lab coordinates with transporters to the total number of lab coordinates and get an estimate. And so far we've seen 9 root transporter locations out of a possible 79, so we can again use a proportion to figure out how many locations to subtract from 11,932. And in this case, 9 out of 79 translates to about 114 out of a possible 1,000 lab portal coordinates that are part of a root system. That might seem like a lot, but the math does work out. So this number is subtracted from 11,932 to give us 11,818 estimated root transporter locations, all separate from any XYZ or karma portal locations. That's only about a third of the size of the total karma portal locations, but it's still pretty large indeed. I mean, I don't even know if the root is that big, but the numbers suggest that it might be.
Well done. So our total is now 1,000 XYZs, 33,696 karma portal locations, and 11,818 root locations. But there are still more locations to add.
Oh yeah? Which ones are those?
Well, the ones from the games, of course. The ones that aren't lab locations, karma portal locations, or root locations.
I see, but considering the numbers we're already dealing with, these numbers won't have next to any effect, will they?
Possibly not, but I'd like to try to be as accurate as possible.
Fair enough. Let's see what we have to work with.
So let's keep this short. If you have questions about these next numbers, let us know in the comments below or on the forum, and we'll help you out. Basically, we made a rough list of the number of extra locations in each game that didn't show up when we were counting before. Compared to what we've been working on before, these numbers are minuscule, so if there are disagreements over these numbers, it won't amount to much in the end. But here's the list. Sub 1, 1 location, Sub 2, 3 locations, Sub 6, 6 locations, Sub 7, 4 locations, Sub 9, 5 locations, Sub 10, 16 locations, and Sub FLF, 2 locations, which all sums up to an additional 37 locations, which is pretty small compared to 33,696, but what can you do?
So, are we missing anything?
Actually, yes. There's another type of portal system we almost forgot about, the original Edge portal network. Let's take those into account, shall we?
Well, I don't see why not. We've come this far.
Okay, so the only hint we really have to work with is a secret from Submachine 6 that has the note Portal Prototype 2 of 32. The only way I can see of interpreting this so that we have some definite number to work with is to assume that this specific portal is the second of a total of 32. So let's say that there are 32 more locations, we have to subtract the 3 that we've already seen so far, which leaves us with 29 edge locations, plus 37 from the games, plus 11,818 root locations, plus 33,696 karma portal locations, plus 1,000 XYZs, and finally I think we've reached the end, which is good, because the batteries in my hologram projector are almost dead.
Oh wait, you're not actually here?
Of course not! I just sent a portable mental stream to you so I could project myself into your surrounding space.
Huh. I see. I didn't even know you could do that. Was there anything wrong with trying to actually be here and present?
Well, first off, of course I can do that. And second off, there is a slight problem with me trying to be where you actually are, wherever that is. And that's because it would require me going outside.
I completely understand. Oh, well, that was abrupt. It's a shame we were on such a roll, too. LT, if you can still hear me somewhere, can you still hear me? Well, I guess not. I would like to say thank you for all the work that you've done to help the community with this question. It'll definitely be of much help, as we'll see in a second. Now let's go calculate this total. The total amounts to this number. 46,580. That's the estimated number of locations we've calculated with the information we have. That's an absurdly huge number. It almost seems unreal, and perhaps it's not, but we still have work to do. Sure, it's nice to have this mind-boggling number to play with, but what can we do to actually visualize this? Let's take a look.
Okay, now I'm interested.
Let's do a quick recap. So far, we've been able to calculate with reasonable certainty how large the subnet's expanse may be when it comes to places we can reach by any means of portal, transporters, or just through the games in the series so far. We're working our way to visualizing how big this subset of the entire subnet is, called the observable subnet, and now we have a good estimate for how many locations take up a decent portion of this overarching region. So now it's time to get even more specific and to actually start attaching real-world measurements to these locations. If these locations actually existed, how much real-world space would they take up? The first place to start for this is to realize that locations are made of rooms, which are roughly shaped like cubes. So if we can decide on how large a cube is, then we can make progress. Unfortunately, we run into a significant problem right away. The size of a cube in the Submachine series varies greatly between locations. If you compare any two locations to each other, you'll notice that we have doorways all of different heights, objects that seem to be just a bit too big or too small for their surroundings, and elements that don't seem to consistently match up to a uniform scale. In fact, you can even see that some rooms have visually more space in them than others. And as significant as this is, we obviously can't blame Mateusz Skutnik for failing to get every pixel correctly in proportion with its surroundings, so we'll have to do some guesswork and averaging of things together. We have a few options. Either we can go through all the locations we've seen so far and make guesses about how much volume is in every single cube, and then add all the cube volumes together, which would be possible to do if I had all the time in the world, which I don't. Or we can make things more simple and keep ourselves sane by picking one type of location and using its calculated cube volume as a standard for the entire subnet. I prefer the latter method. The standard room that I'll be using is a basement room, as it's simple to calculate and we know that the subnet itself has a history of creating these types of rooms, so it's implied that the subnet uses the architecture as a sort of template. It also tends to be on the smaller side, which you can tell just by looking at it visually compared to other locations, and this means that our total measurements will be a conservative estimate. But that's okay, because the sizes that we'll end up with will still probably be freaking huge, so I feel the point will get across quite nicely. Now, the visual clue that I'm going to use to determine the size of a basement cube is the doorways. A typical doorway used by normal-sized humans ranges from about 78 to 80 inches in height, with small variations coming from the fact that the doorways actually tend to be a bit taller in some countries than others. However, this height of 78 to 80 inches actually is roughly equal to a much nicer measurement that we'll use, and that numbered measurement is about 2 meters. A little bit of examining a basic basement room and shifting some lines around shows us that using this measurement, we find that the length of the side of the room is about 3.455 meters tall, or around 11.5 feet. That's about 3.5 feet taller than the average room in the real world. For simplicity's sake, we'll round this to 3.5 meters. And just in case you were interested, this makes the iconic lab portal stand at around 2.622 meters, or about 8.5 feet tall. That's taller than an average room, which stands at about 8 feet, and it has a width of 2.144 meters, or about 7 feet wide. I never really stopped to consider how big the portals might be, but now seeing those numbers, I think they're incredibly huge. Imagine building these things. Anyway, back to the task at hand. We now know that a cube room is about 3.5 meters in length, and cubing this measurement will give us the average volume of a room in the subnet. The result is about 43 cubic meters. Now what we have to do is extend this base measure to the rest of the rooms in any given location. But in order to do that, we have to know how many rooms are in a location. So this is the part where I actually am willing to go and average all the locations together to see what is the average number of rooms per location. A tiny bit of math later, we can find out that out of what we've seen so far, the average location is made up of 9 rooms. However, we must be careful. In fact, averaging these rooms together is not the best way to go, because if you plot out the number of rooms for each location, most of them are not that large, and there are several outliers, like the pyramid and the temple for example, that pull this number up. So it would be more adequate to take the median of all these locations, which gives us a median of not 9 rooms, but 5. As you can see, that's a pretty significant difference. Now that we've determined the average location size is 5 rooms, we can go about this next calculation in 2 different ways. We can multiply 5 by the average volume of a room, and then multiply that by the number of locations. Or, we can multiply 5 by the number of locations, and then multiply that by the average volume of a room. Either way, we get the same answer, but I'm going to use the second way because what that allows us to do is have the total number of rooms before we factor in actual volumes. So 5 rooms per location multiplied by 46,580 locations gives us 232,900 different cubes in this subnet to explore. Now that we have this number, we'll be able to manipulate it once we start talking about volume. And now for the grand total volume of these rooms. 232,900 cubes multiplied by 43 cubic meters per cube is equal to 10,014,700 total cubic meters of subnet space. That is a very large number, but let's take a look at how large that number truly is. Now here is where the fact that we don't know what the subnet actually looks like and what form it takes works against us. You can take these 232,900 cubes and arrange them in various ways. Larger cubes, spheres, prisms, the whole works. However, since we have this magical substance called the void, which is, as far as we know, just literal space between locations, it basically proves that these locations are probably arranged in some sort of large cloud. But just for a baseline reference, let's take the void out and fit all these locations together in a giant supercube, pretending that they would find a way to interlock perfectly. The length of the supercube's side is the cube root of the total volume, and the cube root of 10,014,700 cubic meters is 216 meters long. Well, suddenly that doesn't sound so big anymore. If you're driving in a car at about 60 miles per hour, or around 100 kilometers per hour, the amount of time it would take for you to reach one vertex to another on this supercube of all the subnet locations estimated so far is about 7.776 seconds. You can drive from one end of the subnet supercube to another in a less amount of time than most people spend brushing their teeth. Here's a rough estimate of how big this cube would look compared to a floor plan of a 400-meter running track. So what happened to this vast expanse that we call a subnet? Why does it all of a sudden seem so small? Well, with this model, we have to keep in mind that we assumed that all the locations interlocked perfectly with no spaces in between, and we know that this is far from the case. We also don't know that the subnet locations are arranged in a cube. Rather, it's more likely that they are arranged in some sort of cloud, with varying densities of both locations over a given space, as well as varying densities of possibly the void itself. Now this is the part where cold hard math begins to break down, and we have to resolve to true theorizing. Keep in mind, throughout this whole time we're talking, there are several factors that I of course have to shave off when approaching a final answer, because there are just too many weird variables to keep track of, and some that I or anyone else don't even know exist. So let's do this relatively simply. We've already calculated an estimate for a tight cube of all the locations together. Now let's try to find a rough estimate for how large a cloud of locations would be if they were all in average length apart. Locations might be very close together, or even touching in some instances, or they might be farther away than our human eyes can even see. So for the sake of argument, let's find some sort of middle ground, and the middle ground I'll choose is maximum viewing distance, or the farthest distance that your naked eye can see. Since we are using a standard location size of 5 cubes, that means we indeed will only be able to see so far before we're not able to see a location anymore. And this is assuming that the void between these locations is 100% transparent, which we know it's not, but that won't affect our measurements. There's also the issue of the amount of light given off by the locations, making the visibility larger or smaller, but since I don't have a reliable way to calculate that, then I'll leave that variable behind as well. And finally, there's the variable of warped space, which I also have no way to tackle, so let's pretend it doesn't exist for our purposes. These three variables of light, the void, and warped space work in mysterious ways that I cannot begin to fathom or collect data on, so forgive me for putting these variables aside as we try to find a total size of the subnet with a large asterisk on the end. The human eye and any viewing distance has a certain angular resolution, which relates to how far away from an object you can be before any two details become indistinguishable. The angular resolution of the human eye is about 1 arc minute, or 0.02 degrees, which basically means the smallest object we can see at 1 kilometer away is about 0.3 meters across. Now the typical subnet location is much bigger than that. Let's pick a common shape to arrange the 5 cubes in, let's say in a 2x3 configuration. Now of the two different resulting axes, the longer one is about 10.5 meters across, so we would be able to see this subnet location from a distance of about 35 kilometers before it slips out of view. So this puts all of our locations about 35 kilometers apart, which definitely feels more comfortable if we're going to be describing the subnet as vast. Let's keep things simple and lay all these locations out in a Euclidean grid. We could use an isometric grid that is made out of triangles and might perhaps be a bit more accurate, but the math behind that is much more complicated than I'm willing to try to solve, and accuracy is sort of thrown out the window by this point anyway. So in this Euclidean grid, this amount of space in between any two neighboring locations will be 35 kilometers. However, we must also take into consideration the size of the locations themselves. For simplicity's sake, let's take our average location and wrap it in a bubble with a diameter of 10.5 meters and have that be our quote-unquote viewing platform. That means the centers of each of these locations are about 35 plus 10.5 meters, or 45.5 meters apart. Now if we want everything in a cube as before, then we'll take the cube root of the 46,580 locations and end up with about 36 locations per side. With 45.5 kilometers in between these locations, this gives us a new supercube length of 1,592.5 kilometers. Cubing that, we get a new total volume of, hear me out, 4,400,000,000 38,669,578.13 cubic kilometers of both locations and space between them in this subnet. But this is assuming it's a cube. If we want a model that's closer to a cloud, then we can structure it as a ball instead. With the same volume, we can find that the diameter of this cloud, that is the subnet, is much greater than earlier's 216 meters. It is in fact around, after a couple of mathematical formulas that set the volumes of cubes and balls equal to each other. The final grand total is a ball with a diameter of about 1,976 kilometers. I decided to not stop after finding the volume for a reason, because with this diameter in mind, we can now compare this rough estimate of the observable subnet to something else to get a sense of scale, the planet Earth itself. Because why not? Using our rough estimate of the size of the subnet, how does it compare to planet Earth? Here's a basic outline of planet Earth, and here's what we just calculated to scale. Was this about what you were thinking? I think it's pretty cool to have this comparison here. This diameter of 1,976 kilometers is about 25 kilometers longer than the distance from Denver, Colorado to Atlanta, Georgia. As large as this distance is, do we really accept this as vast? Well, what if we want to increase the size? I mean, sure, as it is, it's already pretty large. But what if we want to, say, increase the size by increasing the number of XYZ locations possible that we can visit? What if we expanded the lab portals so that they could have 4 digits instead of 3? After all, there's nobody saying that there isn't more. How does that impact the size of the subnet? Interestingly enough, the answer is not that much. Adding a 4th number makes the number of lab locations jump from 1,000 to 10,000, and if you redo all the math, this only expands the diameter of the resulting ball to about 2,088 kilometers. And just for kicks, let's also do a scenario for 5 digits. The resulting diameter would increase more, and it will do so exponentially every time you add a digit. For 5 digits, you'll see it increases in size quite significantly. Now obviously, the subnet doesn't have to be comparable in size to Earth, but I find it interesting figuring out what would need to happen in order to make it approach that size. But let's stick to our original numbers using 3 coordinates for lab portals. There's one more thing that I would like to explore. Let's say that instead of a ball or a cloud, the subnet is actually a sphere, with all of the locations instead resting only on the surface of a ball. This model would be fitting if we wanted to view the subnet as maybe some sort of Dyson sphere that surrounds Earth instead of the sun, and one that's also full of holes. Is this physically accurate? Probably not, but is it fun to visualize? Absolutely. I invite you to hold on for a few more seconds and try to power through this last and toughest bit of math with me. Here we go. So creating a sphere with 46,580 semi-equally spaced points is very tough to do. The more accurate you get, the harder the math becomes, and the more choices you have to tackle the problem. I was researching concepts like equidistribution, spherical mapping, sphere packing, polyhedral theory, and reading research papers on things like quaternion triangular meshes, Fibonacci lattices, and Vogel's method. I have no idea what any of those things are, but I finally settled on something simple, creating a grid similar to that of a Mercator projection of the globe of the planet Earth. Even though this guarantees that the locations will not be uniformly spaced, especially near the poles, it'll work out because we expect some of these locations to be closer together than others anyway. I had to figure out a way to come up with the right amount of latitude and longitude lines to put on this grid, so I experimented with grids that had only 1 line of each, 2 lines of each, 4 lines of each, and upward from there, always adding an even number of lines and always seeing how many intersection points occurred in each grid, and adding 2 points to cover the 2 poles. After a while, I took to the online encyclopedia of integer sequences and saw that the number sequence lined up with sequence A108100, which was generated by a formula that looked like it fit the math that I was doing. The webpage had a link to a bunch of number totals that fit different inputs of numbers, so I found the total closest to 46,580, which happened to be 46,210, and multiplied the input number by 2 to match the math that I was doing. In this case, the number of lines is 76 times 2, which equals 152 lines in each direction. However, doing this meant that I would always have an even number of latitude and longitude lines, which means that none of those latitude lines would fall on an equator. So to round it out, I actually bumped this number 152 up to 153, which actually fits the given sequence formula with a result of 46,820 locations, which is a bit closer to 46,580. Then, in order to take into account both locations that are more spread out and locations that are more tightly packed than at the equator, I set the distance for 2 locations on the same latitude to be 45.5 kilometers, about halfway between the pole and the equator line, about 45 degrees from a pole. Here we can calculate a rough circumference of the cross-section of the sphere that runs along this latitude line by multiplying 45.5 kilometers by the number of locations on any given latitude line, which is the same amount as the amount of those lines, or 153. Shaving off the fact that the lines in between these locations should be curves instead of straight lines, we get that a resulting diameter of 45.5 times 153, or 6,961.5 kilometers. This is already significantly larger than before. However, the real equator is 90 degrees from a pole, not 45, and a simple sine function function shows that the circumference we calculated is only about 70% of the equator's circumference. So one last proportion bumps this circumference up to 9,845 kilometers, and that means the diameter of this new sphere totals at 9,845 divided by pi equals 3,134 kilometers. So unfortunately, compared to the size of the Earth, which is around 12,500 kilometers, there's no Dyson sphere that caters to Earth to be had here. But that's still a pretty large surface area to be working with. But as said before, we'll stick with our ball that's 1,976 kilometers across and call it quits. Now, just because I've come up with this number and size does not mean that it should be treated as fact by any circumstance. In order to do this, I had to make a lot of assumptions and cut out a lot of variables, and also my significant figures went completely out the window. The actual size of the subnet might not be near this at all if it can even be calculated, and the unmapped wild mess of submachines beyond the outer rim doesn't help at all. In fact, may as well extend the entire size to infinity. And then there's also the loop. All that this was supposed to be was a way to put together as many locations as possible in a simple perspective that hopefully some of you were able to understand. Now trust me, the more variables we added, the worse the math could have gotten. But for now, I'm happy with this end result, as the subnet being this cloud that you could see from space. It's probably not accurate at all, in fact, certainly not, but it paints a nice image in my mind. So, did we answer the question? Did we figure out how large the subnet is? No, but we did explore the possibilities, and we got a chance to flex our theorizing muscles a fair amount. And I believe that's enough for what we needed to do. Little Tornado wasted no time showing the amount of work and thinking he was able to do to achieve his own goals and think about the subnet in his own ways. When he first joined the Skype chat, the first thing that I remembered him talking about in great detail was how many cipher plate locations there might be. Seeing his passion for figuring out the details of the math behind this topic for no reason other than to fulfill his own goals of reaching a possible answer is what moved me to invite him to help me build this episode. I didn't know when it was going to happen other than it was slated after the original topic I had for BTM6, which I had to ditch because the project was weighing me down too much. But I believe this topic instead for BTM6 was a real success. So I would like to thank LT for being an integral part of that success, and I do not regret bringing him on board for this rare opportunity at all. That being said, that's all I have for now. All comments related to the concepts in this video and other connecting ideas are very, very much appreciated and encouraged. If you guys want, I'll try to explain some more of the math that I did, especially in that last part, in the comments below. I hope you enjoyed this venture as much as I did, and as always, this is Apocrypha hoping to see you again sometime down the road. Bye bye.